Welcome back to the deep dive. Today we're plunging into a world where a millimeter, a single degree, or even just one word can quite literally mean the difference between a structure standing strong or, well, collapsing.
Yeah, it's serious stuff.
We're talking about the incredibly precise language of welding. When you're constructing everything from massive bridges to intricate machinery, the clarity of communication backed by, universally understood terminology is absolutely critical. Safety, quality, innovation.
Yeah.
It all relies on it.
It's pretty wild how a field that seems all about sparks and sort of brute force relies so heavily on such exact definitions.
Right.
It's not just about getting the heat right. It's about speaking the same language down to the tiniest detail.
That really emphasizes the precision involved. So our mission today is to, cut through the jargon, give you a shortcut to being well-informed about the fundamental terms, joint types, weld features, preparation techniques in welding. We've pulled insights from established standards like BS 499-1, BSEN ISO 15607, AWS D1.1, and ISO 6947. These are basically the comprehensive glossaries and visual guides that the industry relies on. Ready to unpack this?
Absolutely. Let's start with the very basics.
Yep.
When we talk about welding, what are we actually saying?
Good question.
We're talking about an operation that permanently joins two or more parts. This union, it's created by applying heat, pressure, or sometimes both. And the key is ensuring the metal forms a continuous, unbroken piece, almost like it was always one.
Like they've merged completely.
Yep. Exactly. The AWS standard, for instance, calls it a localized coalescence of metals. Now, coalescence sounds a bit fancy, doesn't it?
A little bit, yeah.
But really, it just means two things coming together to form one. Think like two drops of water merging. But here, it's super precise and only happens in a tiny spot right where you apply the heat or pressure.
Okay, so if welding is the action, the process of joining, what exactly is a weld itself? Is that like the finished product?
That's a great distinction to make. Yeah. A weld is simply the actual union. It's the metal pieces that result from that welding process. Think of it as the solidified metal that makes the connection.
The physical thing left behind.
Precisely. And then there's the joint. This is the specific connection point where the prepared components come together. The AWS defines it as the junction of members.
Okay.
While the BSEN standard calls it a configuration of members. You can see slight nuances in how different standards phrase things, but the core meaning is the same. It's where the connection happens.
So it's like the difference between saying I'm building a wall and this is the wall, and then the joint is where the bricks actually meet. That really clarifies it.
Good analogy.
Now, let's clear up something that often confuses people. Brazing versus braze welding.
Yeah.
What's the key distinction there? Because they sound so similar.
Yeah, they do. And this is a really important point for clarity because they're fundamentally different in execution, in how you do them. Brazing is a process where you join metals using a molten filler metal. But here's the thing. It's drawn into the joint by capillary action.
Capillary action, like water wicking up a towel.
Exactly like that. Or how sap climbs a tree. It's that natural pulling of liquid into tiny spaces. The filler metal melts above 450 degrees Celsius. But here's the crucial part. It always melts significantly below the parent material's melting temperature. The parent metal itself doesn't melt.
Okay, so capillary action is key. And the filler metal melts below the parent metal temp. Got it. What about braze welding then? Where does that fit in?
Right. Braze welding is the lower melting point than the parent metal. However, it doesn't rely on capillary action.
Okay.
Instead, you're sort of building up the filler metal, almost like infusion welding. But crucially, you're not intentionally melting the parent metal.
So you're adding filler, but not melting the base.
Correct. So the key differences are no capillary action, and you deliberately don't melt the base material, unlike what you typically do in fusion welding.
Fascinating how that subtle difference in process leads to a whole new term and application. It's like, it's not just what you're adding, but how it gets there.
Precisely.
Let's move on to the actual connections themselves, the joint types. Our source material highlights 6 main types. How do the pieces of metal physically meet to be joined?
Great question. Understanding these basic meeting points is fundamental to all welding. It defines the geometry.
Okay.
First, imagine 2 pieces of metal laid end to end, almost perfectly aligned. That's a butt joint. The parts are basically flush, forming a very wide angle where they meet, maybe 135 to 180 degrees, almost straight line.
Flat against each other.
Right. Next, picture a T shape. That's a T-joint. You have the end or edge of one piece meeting the flat face of another. The angle is usually greater than 5 degrees, up to 90 degrees inclusive. Think of the classic T. Then there's the corner joint. This is where the ends or edges of two parts come together to form an angle that's, well, open, but less than a perfect right angle and more than 30 degrees. Think of the corner of a box before it's fully closed, between 30 and 135 degrees.
Okay, like an L shape, but the angle can vary a bit.
Exactly. An edge joint is pretty straightforward. Two pieces meeting along their edges, almost parallel to each other. The angle is very small, 0 to 30 degrees.
Right beside each other.
Yep. The cruciform joint is quite specific. Two flat plates or bars welded at right angles on the same axis to another flat plate. Imagine a cross shape formed by plates.
Like a plus sign made of metal strips.
That's a good way to picture it. And finally, the lap joint. This involves two overlapping parts, much like two sheets of paper overlapping. The angle here is very slight, 0 to 5 degrees.
Okay, those are the 6 main ways they meet. So we've got the basic connections covered, but then these joint types can be combined with different weld types for various applications, right? Like you might have a butt-welded butt joint, or a fillet-welded T-joint, or even a compound-welded lap joint. It really shows the versatility in design when you start putting these concepts together.
Exactly. The joint sets the geometric relationship, the layout, and the weld type defines how those pieces are actually fused together.
Right.
And speaking of weld types, let's delve into some specific configurations.
Okay, here's where it gets really interesting for me. You know, I always pictured welding as adding more metal, but then I hear terms like autogenous weld. How does that even work without any filler material?
That's a great point, and it catches people out. An autogenous weld is indeed a fusion weld made without any added filler metal. You're literally just melting and fusing the base metal itself.
Just melting the two pieces together.
Pretty much. Think of processes like TIG, plasma, electron beam, laser welding, or even oxy-fuel gas welding in some cases. The base material becomes the weld metal.
No filler. That's the key there. Okay. And then we have slot welds and plug welds. How do those differ, and why would you use a hole to make a weld? Seems counterintuitive.
Well, the reason you use a hole is often to join overlapping components where maybe you don't have access to the edge, or you need a very specific type of anchor point between the two layers.
Oh, okay.
So a slot weld is made between two overlapping components. You run a fillet weld around the edge, the periphery, of a specifically shaped elongated hole, a slot in the top component. This joins it to the surface of the other component that's exposed through that slot.
So you're welding around the inside edge of a slot.
Exactly. A plug weld is similar, but it's made by completely filling a circular or oval hole in the top component with filler metal. This joins it to the overlapping component exposed through the hole.
So filling the hole completely.
Right. The main distinction is simply the shape of the hole slot versus circle or oval, and how the weld metal is deposited to achieve that connection through the overlap.
So it's about using those openings to create a strong anchor between overlapping parts. Makes sense.
Mm-hmm.
But how deep does that connection go? That brings us to another absolutely crucial aspect of weld integrity: penetration. What's the difference between a full penetration weld and a partial penetration weld?
This is indeed crucial, yeah, because it directly impacts the strength and reliability of the joint massively.
Right.
A full penetration weld, often called a complete joint penetration or CJP weld, especially in the US standards,
CJP, right.
means the weld metal fully penetrates the joint. It achieves complete fusion all the way through the material thickness. Essentially, the weld goes from one side of the joint completely to the other, creating a solid, continuous bond right through.
And a partial. Logically, it doesn't go all the way through.
Right, exactly. A partial penetration weld, or PJP, is a welded joint where the weld metal does not extend through the entire thickness of the joint. There's a portion left unfused.
Why would you ever want that? Isn't full always better?
Not necessarily. The significance here is profound. CJP welds are generally required for critical structural applications where maximum strength and integrity are paramount. Think bridges, pressure vessels. They provide continuous strength throughout the entire thickness.
Makes sense for critical stuff.
But PJP welds might be perfectly fine where the loading isn't as severe, or where specific design calculations allow for a less than full thickness connection. Maybe it saves cost or time. It's all about matching the weld type and penetration to the expected load and the design requirements.
It's all about matching the weld to the load. That brings us to material compatibility, which sounds like it could get complicated pretty quickly. How do we classify joints based on the materials involved? Are we talking steel on steel or something else?
You're right. This classification is very important for predicting how the weld will behave and for selecting the right welding procedures and filler metals. It gets tricky when materials differ.
So what are the categories?
Okay, first, a homogeneous joint. This is the simple one. It's where the weld metal and the parent material are essentially the same stuff. They have no significant differences in mechanical properties or chemical composition. An example would be welding two standard carbon steel plates together using a matching carbon steel electrode, like welding like.
Easy enough. What's next?
Then there's a heterogeneous joint. Here, the weld metal and the parent material do have significant differences. A classic example is repairing a cast iron part using a nickel-based electrode. You're putting something quite different into the original material.
Why would you do that?
Often for specific properties, like maybe the nickel electrode handles the stresses of welding brittle cast iron better or provides better machinability afterwards. But it means the properties across the joint aren't uniform.
Okay, so weld metal different from base metal. And the third type?
The third type is a dissimilar or transition joint. This is where the parent materials themselves have significant differences in properties or composition. For example, welding a carbon steel lifting lug onto an austenitic stainless steel pressure vessel.
Ah, so joining two completely different base metals.
Exactly. Stainless steel, as you might know, behaves very differently from carbon steel. Think corrosion resistance, how it expands with heat. Lots of differences. This classification is vital because it dictates the complexity of the welding procedure, the filler material choice, which often has to be compatible with both base metals, and how the joint will perform under various conditions like temperature changes or stress.
So many layers of precision. Okay, once a weld is actually complete, it has its own anatomy, right? Almost like looking at a cross-section of a tree trunk. What are the key features we need to understand in that completed weld zone?
Absolutely. This is where we deconstruct the final product to understand its internal and external features. It tells us a lot about the weld quality.
Lay it on me.
Okay. First, you have the parent metal.
Yeah.
That's simply the base material being joined. Easy.
Right.
Then the filler metal, any additional material that was added during the welding process.
The stuff you feed in?
Yep. The weld metal is all the metal that was melted, both filler and any melted parent metal, and then solidified and retained in the weld itself.
Okay, the actual fused bit.
Right. Surrounding that, and this is super important, is the heat-affected zone, HAZ. This is the part of the parent metal that got hot enough during welding to change its metallurgical structure, its properties, but crucially, it did not actually melt.
So it was cooked but not melted. Why is that important?
Because this zone's properties can be significantly altered. It might become harder and more brittle or sometimes softer depending on the metal and the cooling rate. This change can really impact the overall strength and toughness of the joint. It's often where failures initiate if not controlled properly.
Wow, okay. HAZ is critical. What else?
The fusion line is simply the boundary between the fully melted weld metal and the heat-affected zone. The border, yeah.
Oh.
The entire weld zone comprises both the weld metal and the HAZ. It's the whole area affected by the welding operation.
Got it. What about the outside?
Good point. The weld face is the surface of the fusion weld you see on the side it was made, the top surface.
What you look at when you inspect it visually.
Exactly. The root is the deepest part of the weld, the zone on the side of the first weld pass that's furthest from where the welder was actually working. Think of it as the bottom of the V or U groove.
The very bottom of the joint penetration.
Correct. And then there's the toe. This is a tiny, often overlooked part of a weld, but potentially the Achilles heel of a structure. Seriously. The toe, why is it so critical? It's the critical boundary where the weld face meets the untouched parent metal, or sometimes between adjacent weld runs. This isn't just a boundary, it's a geometric discontinuity, which means it's a natural point of high stress concentration.
Like a sharp corner?
Exactly like a sharp corner. Imagine a perfectly smooth ramp versus a jagged cliff edge. That's the difference between a well-blended toe and one that's just asking for a crack to start, especially under fatigue or if there are residual stresses.
So smooth transition is key.
Absolutely essential. To reduce stress concentration, toes must blend smoothly into the parent metal surface. The ideal blend angle might be, say, 20-30 degrees. Compare that with a pour blend, maybe an 80-degree angle. That isn't just pour, it's an invitation for catastrophic fatigue failure or things like cold cracking. It's a powerful reminder that in welding, the smallest details can carry the heaviest load, literally.
Wow, that toe detail is absolutely critical. I can really see why smooth blending is essential, especially for anything under stress or vibration. It's not just about initial strength, it's about longevity.
Spot on.
Now, before we even strike an arc or light a torch, there's the preparation, getting the edges ready. What are the features of weld preparation that determine how successful the weld will be? This sounds like setting the stage properly.
It absolutely is. This is where the foundation is truly laid. Good preparation makes good welding possible. Bad preparation, well, it makes it difficult or impossible.
So what are we measuring?
Several key things. The angle of bevel is the angle at which the edge of a component is prepared, like shaving it down. For example, for a common V-shaped prep, this angle on each piece might be around 25-30 degrees. For a U-shaped prep, it's often a much smaller angle, perhaps 8-12 degrees. These angles are incredibly precise and depend heavily on the specific welding process, the material, the thickness. It's about creating that perfect groove for fusion.
And the total angle.
It's the included angle.
Yeah.
It's the total angle formed between the two prepared fusion faces of the parts when you bring them together. For symmetrical V or U preps, it's simply twice the bevel angle. So a 30-degree bevel gives a 60-degree included angle.
Okay. What about the bottom of the groove?
Crucial area. The root face, sometimes called the land, is the unbeveled portion at the very bottom of the joint preparation. For a full penetration carbon steel weld, it's typically a tiny flat sliver, maybe 1-2 millimeters wide.
Why have that flat bit? Why not bevel to a sharp point?
Because that root face is incredibly critical for controlling how the root of the weld fuses. It helps support the molten weld pool on the first pass. If it's too small or sharp, you risk burn through, the metal just falls out. If it's too large, you risk lack of penetration. The weld doesn't get deep enough. It's a fine balance.
And the gap between the pieces.
Also critical. The gap, or root opening, is the minimum distance left between the edges or ends to be joined, usually 1 to 4 millimeters for full penetration carbon steel welds. Like the root face, it works together with it to control that root fusion, prevent burn through, and avoid lack of penetration. Too tight, no penetration. Too wide, burn through.
A real sweet spot needed there. What else for J or U preps?
For J or U preps, you also have the root radius. That's simply the radius of the curved portion of the fusion face at the bottom of the U or J shape.
Makes sense for a curved shape.
And sometimes there's a land in a J or U prep. That's a short, straight portion between the root face and the start of the root radius. It can sometimes be 0, especially, say, in MIG welding for aluminum alloys. It just gives another variable to control the root conditions.
It's incredible how specific those dimensions are, down to the millimeter, fractions of an inch. And I imagine there are different types of weld preparations depending on the application. You wouldn't just use a V-prep for everything, surely.
Absolutely not. The choice of preparation is a complex balancing act. Cost, time, material, thickness, access, expected stresses, they all play a role.
So what are the main types?
Starting with the simplest. Square butt preparations. An open square butt, meaning there's a gap, is used for thin materials where you can weld from one or maybe both sides without beveling. A closed square butt has no gap, the edges touch. That's generally not recommended because it's very prone to lack of penetration issues.
Okay, so square preps for thin stuff, usually with a gap.
What about thicker materials? That's where bevels come in. We have V preparations. A single V, where only one side is beveled, is very common. It's relatively cheap and fast to produce, often just by flame or plasma cutting. Simple.
But maybe not ideal for really thick stuff?
Exactly. For thicker plates, a double V is often preferred. You bevel both sides. Why? Several reasons. It requires significantly less filler material compared to a single V of the same depth, which saves time and money. It also helps balance out the welding heat and shrinkage, leading to lower residual stresses and less angular distortion in the final product.
You're welding more symmetrically.
Less warping, basically.
Less warping, yeah.
Yeah.
You can even have an asymmetric double V where maybe one side is 2/3 the depth and the other is 1/3. This allows for a more balanced welding sequence. Weld the deep side than the shallow side that can further reduce distortion.
Clever. What about U-preps? You mentioned those. Right, U-preparations. These are typically produced by machining, which is slower and more expensive than cutting a V, but it gives much tighter tolerances and a smoother surface. They're often used for even thicker plates than V preparations because the U-shape requires even less filler metal for the same depth.
Less volume to fill.
Exactly. Less volume means lower heat input overall, lower residual stresses, and less distortion, which becomes really important on very thick sections. And like the preps, you can have single U or double U preparations.
Okay, V and U preps. What about backing?
Good point. Backing strips are often used, especially with single V preparations on thicker material where you need full penetration but welding from one side. They're essentially a temporary or permanent support placed behind the root of the weld joint.
What do they do?
They support the molten weld pool, allowing you to use higher welding current for better productivity and ensure full penetration without risking burn-through where the metal just falls out the back.
Permanent or temporary, you said?
Yes. Permanent backing strips are usually made of the same material as the base metal and are tacked in place. They become part of the joint. But they can sometimes cause problems later. Poor fatigue resistance because of the notch effect at the edges, potential for crevice corrosion between the strip and the base metal, and they can make non-destructive testing checking the weld quality more difficult.
So temporary might be better sometimes.
Often, yes. Temporary backing can be made of copper, which doesn't fuse easily with steel, ceramic materials, or even special flexes. They do the job of supporting the weld pool and are then removed afterwards, leaving a cleaner root profile.
Interesting trade-offs there. And finally, bevel and J preps.
Right, bevel and J preparations. These are like V and U preps, but only one of the two pieces being joined is prepared. The other piece usually has a square edge, so you have single bevel, single J, double J.
Why use those?
They can be used on T-joints or corner joints, for example. The main advantage is that only one component needs edge preparation, which can be cheaper and faster. It also allows for a bit more tolerance for small misalignments between the parts. Like the V and U preps, double preparations, double bevel, double J, are generally recommended for thick sections to reduce weld volume and distortion.
So many choices, each with its own set of pros and cons related to cost, speed, quality, and the specific application. It really emphasizes the engineering thought that goes into designing even a single welded joint.
It really does. There's no single best prep. It's always about the context.
Speaking of choices, let's talk about the specific sizing and shape of the two main weld types, butt welds and fillet welds. How do we define the size of a butt weld?
For butt welds, the key dimensions relate to the thickness. We primarily talk about the design throat thickness versus the actual throat thickness.
What's the difference?
The design throat thickness is the nominal dimension used for strength calculations, usually specified on the drawing. The actual throat thickness is the real physical dimension of the thinnest section through the weld. Generally, the actual throat thickness is the design throat thickness plus any excess weld metal or reinforcement on the weld face.
So the actual is usually bigger, unless
the weld is ground flush with the plate surface. In that case, the actual throat thickness equals the design throat thickness. Also, for butt welds joining plates of different thicknesses, the design throat thickness is typically considered to be the thickness of the thinner plate.
Okay, that makes sense. And within a butt weld, you mentioned runs and layers.
Yes. A run is the metal deposited during one single pass of the electrode, torch, or blowpipe along the joint. A layer is basically a stratum or level of weld metal that might consist of one or more runs laid side by side before moving up to the next level.
So multiple runs can make up one layer, and multiple layers fill the joint.
Exactly. Especially in thick V or U preps.
Got it. Now, fillet welds. They seem a bit more complex in terms of size and shape, just looking at the typical diagrams.
They certainly are geometrically, and the shape is hugely important for performance, as we touched on with the toes. For fillet welds, we define three key dimensions.
Okay.
First, the actual throat thickness. That's the shortest distance from the root of the weld, the corner where the plates meet, out to the weld face.
The thinnest part through the weld triangle.
Essentially, yes. Second, the design throat thickness. This is the minimum required dimension used for design calculations, and it's usually labeled A on drawings. Third, the leg length. This is the distance from the root out to the toe of the weld along each leg of the triangle along the parent plates. It's usually labeled Z on drawings.
So A for throat, Z for leg. Is there a simple relationship?
For the most common shapes, like a perfect miter fillet weld, which has a flat face at 45 degrees and equal leg lengths, or a convex fillet weld where the face bulges outwards.
The ones that look like a simple triangle or a slightly bulging triangle?
Right. For those, there are simple formulas based on trigonometry. The design throat A equals approximately 0.7 times the leg length Z, or rearranging it, leg length Z equals about 1.41 times the design throat A.
Okay, 0.7, 1.4 are useful numbers there.
They are, but, and this is absolutely crucial, These simple calculations are only valid if the two fusion faces, the plates being joined, form an angle between 60 degrees and 120 degrees, usually 90 degrees for a T-joint.
What happens outside that range?
If the angle is sharper than 60 or wider than 120 degrees, those simple factors, 0.707, 1.41, don't work anymore. You have to use different factors based on the specific angle to calculate the effective throat for strength. So it's not always simple geometry. The angle matters a lot.
Good warning. What about different fillet weld shapes? You mentioned miter and convex.
Yes, shape is critical. A miter fillet weld has that flat weld face and typically equal leg lengths. It's like a perfect 45-degree triangle face. A convex fillet weld has a face that curves outwards, it bulges. This means its actual throat thickness is greater than the design throat thickness calculated from the leg length. Might seem stronger, but the transition at the toe might not be ideal. Which brings us to the concave fillet. This one has a face that curves inwards, it's slightly scooped out.
Why is that one so desirable?
Because this shape is highly desired. Why? Because its smooth, gradual blending between the weld face and the parent material significantly reduces that stress concentration right at the toes that we talked about earlier.
That sharp corner effect is minimized.
Exactly. Imagine a gentle curve meeting the plate versus a sharper angle. That concave curve makes it ideal for applications subjected to cyclic loads, vibrations, fatigue. Anywhere those stress points could lead to cracking over time. Better fatigue life.
Makes perfect sense. Any other shapes?
There's the asymmetrical fillet weld, which simply has unequal leg lengths. Z is different on each plate. The standard simple formulas for A and Z don't apply directly here either.
Okay.
And finally, a deep penetration fillet weld. This is a special type where you achieve deeper than normal fusion penetration into the root corner. These are typically produced using high heat input processes like submerged arc welding or maybe mag welding with spray transfer mode.
What's the benefit of that?
The main benefit is that you might achieve the required effective throat thickness with less deposited filler metal compared to a standard fillet weld. Less metal can mean reduced residual stress and distortion.
Sounds good, but is there a catch?
There is. It requires very careful control, specifically a very constant high travel speed during welding. If that speed varies, you significantly increase the risk of solidification centerline cracking right down the middle of the weld. So higher productivity potential, but also higher risk if not done perfectly.
I can absolutely see why concave fillets are preferred for fatigue-sensitive applications. It's all about spreading that load and avoiding sharp corners.
That's the name of the game for fatigue, yeah.
And then we have compound welds. What are they?
Yes, compound welds are essentially a combination of a butt or groove weld and a fillet weld. They're typically used for T-joints that require full or partial penetration preparation, or sometimes on butt joints between plates of significantly different thicknesses.
So you do the groove weld first, then add a fillet on top?
Usually, yes. The fillet welds are added on top of the groove weld, primarily at the toes. This further improves the blending of the weld face towards the parent metal surface, which, as we just keep emphasizing, is critical for reducing stress concentration at the toes and improving fatigue performance.
Smoothing out that transition even more. Okay, so we've talked a lot about the static aspects, the features, the shapes, the preparation. What about the dynamics of actually doing the welding? Like, how is the welding position described? Is it just up or down or flat?
If only it were that simple. No, welding position, according to the standard ISO 6947, is expressed in incredibly precise terms. It uses angles, weld slope, and weld rotation.
Slope and rotation. Sounds like 3D geometry.
It basically is. Weld slope is the angle between the root line of the weld and the horizontal plane, positive x-axis. Weld rotation is the angle between the vertical plane containing the weld center line and the vertical plane, positive z-axis, in the transverse cross-section. It's a full 3D coordinate system for defining the orientation of the weld joint relative to the welder and gravity.
Wow, okay, that's detailed. But are there simpler terms for common positions?
Yes, thankfully. Those angles define the main standard positions, which are often abbreviated with symbols. These are what you usually see specified.
Welding is basically looking down onto a horizontal surface. Easiest position.
Gravity helps you.
Exactly.
This is for fillet welds. Think of a T-joint sitting normally. You're welding the horizontal seam where the vertical plate meets the horizontal one.
This is for butt welds. The weld axis is horizontal, but you're welding on the vertical face of the joint, like welding the side of a box seam.
Okay, so welding across horizontally,
Right.
Welding upwards on a vertical surface, fighting gravity.
Welding downwards on a vertical surface, gravity is pulling the puddle down.
Up and down seems straightforward enough.
Then overhead.
Welding from underneath a horizontal surface, definitely the hardest.
This is for fillet welds again, like welding the underside seam of that T-joint if it were upside down. These symbols, PA, PB, PC, PF, PG, PE, PD, are essential shorthand in the industry, appearing on drawings and welding procedures.
Got it. Those precise angles and directions tell the welder exactly how to orient themselves and manage the weld pool against gravity. Very important. And what about weaving versus stringer bead? I've heard those terms come up a lot in technique discussions.
Yeah, that's about the technique of how the weld metal is actually deposited during a run. Weaving refers to a transverse oscillation, basically a side-to-side motion of the electrode, or the welding torch nozzle as you move along the joint.
Why weave?
It's generally used to spread the heat out more, create a wider bead, and help fill the joint, especially in wider gaps, or when welding vertical up, PF, to counteract gravity a bit and control the puddle shape.
Okay, so a side-to-side motion. What's a stringer bead then?
A stringer bead, on the other hand, is a run of weld metal made with very little or practically no weaving motion. You're basically just dragging the electrode or torch straight along the joint line. This creates a more narrow, consistent, and often deeper penetrating bead compared to a weave bead made with the same settings.
So straight versus zigzag, essentially.
That's a simple way to think about it, yeah.
Yeah.
The choice often depends on the position, the joint type, the material thickness, and what you're trying to achieve with that particular pass.
This brings us perfectly to the ultimate synthesis of all this knowledge, the factors that impact the choice of weld preparation. It really feels like the art of the possible, where all these precise definitions, joints, welds, materials, positions come together for practical application. So if I'm designing something that needs welding, what influences my choice of weld preparation? Because it seems like there are endless options.
You're absolutely right. It's not a simple choice. This is where all the previous terms really come into play. Many factors dictate the optimal weld preparation, and it's a critical design decision with big implications for cost, quality, and performance.
So what's factor number one?
First, the welding process itself. Different processes like shielded metal arc welding, MMA or stick, gas metal arc welding, MIG-MAG, tungsten inert gas, TIG, submerged arc welding, SAW, electron beam welding, EBW, have very different heat characteristics and capabilities.
How does that affect the prep?
Well, high heat input, high deposition rate processes like SAW might allow for, say, larger root faces and narrower included angles because they can penetrate more easily. This means less weld metal is needed, which can reduce distortion and increase productivity. But with any process, that root gap and root face combination, as we discussed, is still absolutely critical. Get it wrong, and you risk burn-through or lack of penetration, regardless of the process power.
Okay, so the process matters a lot. What else?
Second, the preparation method. How are you actually making the bevel or groove? Are you machining the edge? That gives nice, clean, tight tolerances, but it's generally slower and more expensive.
Versus
thermal cutting, like flame cutting or plasma cutting. That's usually much faster and cheaper, but it typically results in larger tolerances, maybe a rougher surface, and can make the fit-up and setup for welding a bit harder to control precisely. It's a classic trade-off between precision and cost speed.
Makes sense. Third factor.
Third, access. Can the welder get to both sides of the joint easily? Or is access restricted to only one side? Single-sided access is common for thinner materials, or in confined spaces like welding pipework from the outside only. Double-sided access is preferable for thicker materials, as it allows for double V or double U preps, which, as we said, reduce weld volume and distortion. So access fundamentally changes your preparation options.
Got it. Access dictates single versus double prep. What else?
Fourth, the type of joint. We talked about butt, T, corner, etc. A simple corner joint might inherently need one edge offset slightly for good access. Lap joints and square-edged butt joints on thin material might not require any bevel preparation at all beyond just cleaning the edges properly. The geometry itself plays a role.
Okay, number 5.
Fifth, the type of parent material. Different metals and alloys behave differently. For instance, some stainless steels are prone to distortion, so you might choose preparations with reduced included angles and maybe increased root faces to minimize the heat input and shrinkage stresses.
And aluminum.
Aluminum often needs the opposite. It conducts heat so well and can be prone to lack of sidewall fusion if the angle is too narrow. So you often need larger included angles for aluminum, perhaps 70-90 degrees compared to maybe 35-60 degrees for steel, just to ensure the weld properly fuses to the sides of the joint. Material properties dictate the geometry.
Wow, big difference there. 6th factor.
6th, the thickness of parent material. This is a major driver. As we've said, thicker plates generally benefit from double preparations, double V, double U, to reduce the total volume of weld metal needed. Less metal means less welding time, lower cost, and crucially, less shrinkage and distortion.
Are there other strategies for thick plates to reduce distortion?
Yes. Besides reducing weld volume, by using smaller included angles, tighter root gaps, larger root faces, or switching from V-preps to U-preps, using those asymmetric V-preps we mentioned can help. By welding the deeper side first, then back gouging or grinding the root of the first weld before welding the second, shallower side, you can help balance the shrinkage forces and significantly lower the final angular distortion.
Clever sequencing. Okay, what's next?
7th, welding position. The position you have to weld in, PA, PC, PF, etc., can influence the prep. For example, a standard symmetric V-prep might work perfectly when welded flat, PA. But if you try to weld that same prep in the horizontal PC position, the molten weld metal might just sag or spill out due to gravity. In that case, an asymmetric preparation might be required, maybe with the lower bevel being steeper, to provide a better shelf to hold the molten pool.
Position affects pool control, so prep needs to help. Makes sense. And finally,
and perhaps most importantly, the type of loading the finished joint will experience in service. Is it just static load, like holding up a shelf? Or is it dynamic or cyclic load, like on a bridge experiencing traffic vibration or machine part that moves constantly?
how does that affect prep choice?
For primarily static loads, things are a bit more forgiving, although certain joint types might still be prohibited, like maybe single-sided fillet welds in some codes if they carry significant load. For T-joints under static load, using a prepared joint, for example, a bevel prep on the T, generally reduces distortions during welding compared to just slapping on a fillet weld without prep.
But for dynamic loads?
For dynamic or cyclic loads, things get much stricter. Full penetration welds are almost always crucial because any lack of penetration, any unfused area at the root, acts as a built-in crack starter under repeated loading. Fatigue failure often starts right there.
So CJP welds are a must for fatigue?
Generally, yes. And as we discussed extensively, those concave fillet profiles are highly preferred for dynamic loads because their smooth blending minimizes stress concentration at the toes, giving the joint a much longer fatigue life. So the anticipated service load is often the ultimate deciding factor in choosing not just the preparation, but the required weld quality and profile.
Wow. It's clear that every single decision, from the choice of material right down to the precise angle of a bevel or the shape of the weld face, cascades through the entire process, impacting the cost, the feasibility, and ultimately the safety and integrity of the final structure. It's a true blend of science and really engineering artistry.
Exactly. It's not just sticking metal together. Each term, each definition, each parameter plays a vital role in ensuring that a welded structure performs exactly as intended, safely and reliably, whether it's holding up a massive skyscraper or connecting a tiny electronic component.
And that brings us to the end of our deep dive into the world of welding terminology. We've journeyed through the foundational terms weld, joint, brazing, braze, welding. We explored the 6 main joint types, distinguished between various weld configurations like autogenous, slot, and plug welds, and the critical difference between full and partial penetration.
We also looked at material compatibility, heterogeneous, dissimilar joints, and then deconstructed the anatomy of a completed weld, focusing on key features like the HAZ and especially that all-important weld toe.
Right. Then we delved into the intricacies of weld preparation, features bevel angles, root faces, gaps, and the different types like V, UJ, and bevel preps, including the use of backing. We covered the dynamics of welding positions using the ISO system and the difference between weaving and stringer beads.
And finally, we tied it all together by looking at the multitude of factors: process, prep method, access, material, thickness, position, and loading that critically influence the choice of weld preparation for different applications.
What really stands out here, for me at least, is how the seemingly small details, that millimeter of root gap, the precise angle of a bevel, the subtle concave shape of a fillet weld's face, have such profound implications. They affect the strength, the integrity, the longevity, the performance of a welded joint, especially under different conditions and loads.
Absolutely. Precision in terminology allows for precision in communication, which enables precision in fabrication. And that precision is ultimately what ensures safety and reliability in engineered structures. It all links together.
So as you reflect on all this detail, maybe consider this. How does this intense level of detailed standardization and definition in welding, a field that literally fuses materials together at high temperatures, reflect a deeper human need? a need for control, for predictability, especially when we're creating structures that demand immense, unquestionable reliability.
That's a great point.
And taking it further, what other areas of life, or maybe other industries, could potentially benefit from adopting such precise, universally understood terminology? But also, what challenges might arise in trying to get everyone on the same page with that level of detail? Something to think about. Join us next time for another deep dive.